Hi everyone, I am Ashutosh Anand from Mechanical Department of NSUT Delhi. Today I will teach you complex numbers and quadratic equations. Have you ever tried finding out square root of negative numbers? What does the calculator says? It says math error. So today we are going to unlock this mystery. What are complex numbers? Why we are using complex numbers? And what are the properties of complex numbers? So let's get back into 16th century when mathematicians were trying to solve cubic equations that require finding out square root of negative numbers. But it was only in the 18th century when the great mathematician Euler discovered iota and defined it as square root of -1. So iota I is under root of -1. On squaring both the sides, we get I square equal to -1. I cube will be minus I, and I raised to the power 4 will be 1 again. So you can see that this cycle repeats, and I raised to the power 5 will be under root of -1 again. So this cycle repeats after every 4 power of iota. So we can solve any power of iota and we can calculate what will be the complex number. For example, I raised to the power 103. We can divide 103 into 100 and 3. 100 is a multiple of 4 and 3 will be I cube minus 1. That's why it will be I. Now, coming back to complex number. What is a complex number? The definition of complex number is that any number of the form a plus ib, where a and b are real numbers and I is imaginary number iota, is called a complex number. Let me write it down. Z, a plus ib. In general, complex number is written as z, a plus ib. So I will tell you one interesting fact, that we can't compare two complex numbers. Like we can't say that one complex number is greater than another complex number and one complex number is smaller than another complex number. For example, you can't compare 3i or 4. Which is greater, 3i or 4? Neither. We can't just compare it. So now we will come how to equate two complex numbers. For example, if there are two complex numbers z1, which is a plus ib, and z2, which is x plus iy. So if we want to equate two complex numbers, we simply have to equate the real parts, which are a and x, and the imaginary parts, which are b and y. So if z1 equals z2, a equal to x, b equal to y. So this is the solution when we equate two complex numbers. Now let's get into the algebra of complex numbers. So in algebra, there are mainly 4 operations: addition, subtraction, multiplication and division. So as you know, subtraction is just addition of a negative number to another number, and division is just multiplication by the denominator. So mainly we have to study addition and multiplication. So starting with addition, if there are two complex numbers z1 and z2, so on adding two complex number, it will be like adding the real part separately and adding the imaginary part separately. So we will simply add the real parts, x plus a, and the imaginary parts. So you can see that it is also of the form a plus ib. So this is also complex number. That is why it follows closure property. Let me write it down, closure. Second property is commutative. So how it is commutative? Because z1 plus z2 is simply z2 plus z1. Therefore addition of complex number is commutative, and similarly it will be associative. And now coming to the additive identity of complex number. What is additive identity? Additive identity is what should be added to a complex number so that the complex number is returned. Like then we just have to add 0 to the complex number and it will return z. So additive identity is 0. Now let me write it down. Additive identity. And the fifth is additive inverse. Additive inverse is what we should add to the complex number such that the complex number vanishes. The result should be 0. So it is that if we add z and minus z, it will be 0. So additive inverse of z is just minus z. So this is the laws of addition. And now coming to multiplication. Multiplication of two complex number is very similar to algebraic multiplication. Let me just write it down. Z1 into Z2 x plus iy into a plus ib. It will be xa plus iya plus xb plus I square b. As you know, any complex number is of the form a plus ib. That is why we will segregate these two real parts and these two complex parts. Okay, so that will be xa, and you know I square is minus 1, that is why xa minus by and I ya plus xb. So it is clearly of the form a plus ib. That is why z1 into z2 is also a complex number. That is why it is follows the closure property. Now coming to the commutative property, z1 into z2 is z2 into z1. That is why it is commutative. Similarly, it is associative. And now coming to the multiplicative identity, like what we should multiply into a complex number such that the answer is same. What we should multiply, that is 1. So 1 is the multiplicative 1, or 1 plus 0i is the multiplicative identity of any complex number. Now coming to multiplicative inverse. What is the multiplicative inverse? It is just what we should multiply to a complex number such that the result is 1. So what should we multiply? It is simply 1 by z. So to solve 1 by z, another concept comes into play, that is conjugate. If a complex number z is a plus ib, its conjugate will be denoted by z bar and it will be a minus ib. And let me show you how it will help us to find 1 upon z. 1 upon z will be then 1 upon a minus ib, and if we a plus ib, then if we multiply the conjugate into the numerator and the denominator, it will be a minus ib upon a minus ib. That would be a minus ib upon a square plus b square. This is the numerator is the complex and denominator is real, and that is why we can write it in the form a plus ib, and that will be a complex number. So this was the conjugate. Now we will study what is the modulus of a complex number. Modulus is just like the magnitude of a complex number, as you must have studied in the vector. If z is the a plus ib, the modulus is denoted by this, and it is under root of a square plus b square. So now we will study some of the properties of modulus and conjugate of a complex number. Let me just double this out. So the first property of conjugate of a complex number is that z bar to the bar will be z again. Okay, then z1 plus z plus minus z2 plus minus z3. Similarly, if you take whole bar, it will be z1 bar plus z2 bar and so on. Similarly, if you multiply two complex number and take bar as a whole, it will be z1 bar into z2 bar. Similarly, if we divide two complex number and take the bar, it will be z1 bar upon z2 bar. Now these were the properties for conjugate of a complex number. Now we will study some of the properties of magnitude or the modulus of complex numbers. modulus of complex number is z1 into z2. Whole modulus will be simply z1 into z2. Similarly, z1 upon z2 whole mod will be z1 mod upon z2 mod, and so on. So these were some of the properties for modulus and conjugate. Now we will study eigenplane. So what is eigenplane? It is a very interesting topic, as to denote any point in the space you must have used coordinate axis. Similarly, in complex numbers, Argand was a mathematician who discovered or gave the theory for how we can represent any complex number in the plane. I will just explain you that if this is a plane, this x-axis is for the real part and this y-axis is for the imaginary part. For example, if there is any complex number 5 plus 3i, let's say 5 plus 3i, then 5 is the real part, we can find it here. 3 is the imaginary part, we can find it here. So this is the point 5 plus 3i, and this is the representation of a complex number in a plane, and this plane is called Argand plane. This plane is called Argand plane, and it has two main symbols. First is modulus of z, that is the distance from the origin. This is simply mod of z, and this angle from the positive x-axis theta is called argument of this complex number. So how do we find the argument of any complex number? We will study shortly, but for now we can say that theta, which is argument z, is simply tan inverse of this upon this. This is simply 3 and this is 5. So tan inverse 3 by 5 is the argument of this complex number. Now let us see what are the argument of complex number in all the 4 quadrants one by one. Okay, let me clear this out. So if a complex number is in the first quadrant, let's say x, this is the argument of that complex number theta. Simply, if a complex number is in this quadrant, theta will be this, the argument will be this, because it is theta argument is defined from the positive x-axis to the complex number, and it is defined between minus pi to pi. So this is the argument. If it is in the third quadrant, this is the argument, and if it is in the fourth quadrant, this will be the argument. So if this is theta, the argument in the second plane will be pi minus theta. It is theta in the first quadrant, and in this, if this is the theta, the argument will be minus pi plus theta. And if this is in the fourth quadrant, it will be minus theta simply. So these are the 4 values of argument in the 4 quadrants. So that was it. And now you must be thinking, where is the use of this argument and where is the use of this modulus? This is highly used in finding out the polar form of any complex number. For example, if a complex number here is in the third quadrant, it will be minus 3 plus minus 5j, let's say, for example 5i. So how can we represent it in the polar form? That is, polar form is in the form of r cos theta plus I sin theta, where r is the modulus of the complex number, which is under root of minus 3 square plus minus 5 square. So r is the modulus of complex number, and theta is the argument of z. What is this argument of z? The shortest distance from the positive x-axis. It will be, we can find it, if this is theta, it will be minus pi plus theta. We can find theta, tan theta. It will be mod of this is 3, this is 5, so 5 upon 3. And from here we can find this argument and we can put it into this. This is the polar form. So these were some of the application of argument and conjugate. Now we will get back to the starting of this lecture, where we have used to where we started to finding out the roots of the cubic equation or roots of the quadratic equation. So let's say we have to find cube roots of unity, like x cube equal to 1. We can just bring x 1 to this side, and we can multiply x minus 1 into x square plus x plus 1 equal to 0. So clearly x equal to 1 is the solution of this equation, but other two solutions of this equation are not real, and here is where the application of complex number come into play. For example, the solution are minus 1 plus minus and root of this is minus 1 plus minus and root of minus 3 upon 2. Okay, so we have defined minus 1 under root as iota, that is we can write 3 into minus 1 under root upon 2 minus 1 plus minus root 3 iota by 2. So these are the two solutions of this equation, and one is the solution of this equation. So these are the three solutions of this particular equation, and that was it. Hope you enjoyed the video. Thank you.